Hey, how about a quick video on the enthralling concept of continuity? In the lower math classes or the lower grades, it was simple. That thing's continuous. That thing's not continuous because it has a space or a break. Well, what we're going to do is we're going to add actually quite a nifty and eloquent definition of continuity for this phenomenon. So I'm going to start off with a definition that you very well could see in a math book. A function is continuous at the point x equals c if the limit as x approaches c of f of x equals f of c and f of c exists. At first, that definition turns you off. You don't like looking at stuff like that, so we'll come back to that. But before that, let's put it into some more common English. A function is continuous at a specific point if the function value and the limit value are equal at that point. Function value and limit value are equal at that point. And of course, that point has to exist. So it might take a little bit for you to soak it in. You may need to pause the video, look at that paragraph, look at this math notation, and come to terms with the fact that they really are doing the same thing. And then I'm going to show you this applied to 3 different examples. So here we have an awkward looking graph, and we're going to check for continuity at 3 locations at x equals -3, x equals 1, and x equals 3. And your eyeballs already tell you continuous, discontinuous, discontinuous. But we're going to show how you can put that into the picky math language. So I'm going to start off with the spot x equals 3, and I'm going to have to move this off the screen, but we're going to be using this definition. Okay, I'm going to actually zoom this out or make it a little smaller. Okay, there we go. So x equals 3, we've got ourselves a jump discontinuity, and we know it's discontinuous, but here's how it fits into that math definition. The function value is 1. The limit value, I have to approach x equals 3 from the right-hand side, and I'm closing in on a value of 3. I have to approach x equals 3 from the left-hand side, and I'm approaching a value of 1. So because the left-hand limit does not equal the right-hand limit, the limit does not exist. So now, according to the definition, my function value and my limit value do not equal each other, thus it is discontinuous. Let's move on to the next one, x equals 1. You know that that is discontinuous. This is a point discontinuity. That was a jump discontinuity. And the way you would put the math definition into there is you would say, well, let's look at the function value. At x equals 1, the function value is 2. Let's look at the limit value. At x equals 1, I would approach from the left side. I'm closing in on a y value of 4. The right-hand limit is closing in on a value of 4. So my limit value is 4. I did informally the left-hand limit equals the right-hand limit. Now I compare my function value and my limit value, and they're not equal to each other, therefore it's discontinuous. This is the math, or the math notation, that's confirming what your eyeballs see. All right, let's finally look at x equals -3, and you know that that is a continuous spot because that's what your eyeballs tell you. But let's see what the math tells you. If I look at the function value, the function's value is 2. As I approach from the left and the right, my y values are closing in on a value of 2. So my limit and my function value are equal, thus it's continuous. And if you wanted to fancy it up a little bit, my limit value equals my function value equals 2. In other words, both the limit and the function value equal the y value of 2, but you don't have to do that. You can do this. If you had to justify continuity in a very formal math setting, this is what you would do. And one final thing before I leave, just in case you needed, oops, that's got to be tough on the eyeballs, a review on the discontinuity vocabulary, point discontinuity, jump discontinuity, and less commonly used, this thing called the infinite discontinuity, which just means you're missing an x value somewhere between here and here because it's an asymptote. An asymptote goes on forever. Catch you later.